we have here Alberto Padovan. Alberto, of course, is from Padova, from Italy, but he spends all his academic career in the US. He studied Buffalo, bachelor, so Buffalo, then PhD at Princeton, and in 2022, then postdoc at University of Illinois. It's Champaign. And recently, just a few days ago, September 1st, tenure track assistant professor at the New Jersey Institute of Technology in Newark. And we met him in London during a conference on machine learning for CFD. And since he's going also to the Ecomas Young Investigators in Italy, his family, it's a great pleasure to have him here today for a talk, since there are close connection in terms of topics with what we are doing here in our group and the system MATLAB more generally. So leveraging oblique projections for model reduction, recent advances in Petrov-Galerkin and non-intrusive formulation. Thank you, Alberto.
Thank you. Thank you, Gianluigi, for the very kind introduction and for the opportunity to speak at today's seminar. So the focus of today's talk is oblique projections for the purpose of model reduction. And I know a lot of you here are experts in the area of model reduction. So hopefully you'll see some stuff that you've already seen before, but also hopefully some new topics. Let me see. How would I?
You have to go back to the slide maybe, or and up and down. Bottom. And you see. Yeah, it's okay. Because now it went out, but okay, yeah, downwards it's you're gonna get.
Okay, great. So
down to forward.
So it won't go back.
You cannot go back.
I don't think I can go back. Okay, so I'm going to try not to mess up and have to go back. So this is the outline of the presentation. I will start with some introduction and motivation. I decided to split the motivation into two components, high level and low level. The first one is introducing the concept of model reduction. Perhaps it's unnecessary for this audience, but nonetheless, why not? And then low level, why oblique projections? And this is really going to be the key of what we're going to be doing downstream for the rest of the presentation. Then we're going to be looking at some Petrov-Galerkin formulations and then some more recent work that I've done on non-intrusive models. Okay, so why model reduction? So physical systems of practical relevance are, as we all know, expensive to simulate, takes a long time, even on modern high-performance computing clusters, and this inhibits scientific discovery and computer-aided engineering design. And so the field of model reduction attempts to reduce this computational cost in one of two ways. We can basically either use data or the underlying governing equations to reduce the computational cost and hence promote scientific discovery and computer-aided design. So what does a ROM look like? So when we talk about reduced order models, implicitly there's always like an underlying full order model, henceforth the FOM. So this is a very high-dimensional set of ODEs that is governed compactly by this equation. Q is the state and U is the control input. So if we're talking about fluid mechanics, Q is the state, for instance, like the spatially discretized velocity, density fields, and so forth on a computational grid. And U is an external input in the form of boundary forcing, volumetric forcing, and so forth. And so this is what a ROM looks like. It has three fundamental components. It has an encoder, a decoder, and then in the middle, so-called latent space or reduced order dynamics. And so the encoder and decoder are possibly nonlinear maps that take us from the high-dimensional space to the low-dimensional space and vice versa. And the latent space dynamics here allow us to advance the latent space vector forward in time. Okay. And so clearly, those three components determine whether the model is going to be accurate or not. But the choice of encoder, decoder, and dynamics is objective driven. And what I mean by that, the type of model that we're going to compute is dependent on what we want the model to do. So if we want to solve inverse problems, then we're going to be choosing encoders and decoders in a certain way. If we want to make forecasts, then we might look for other type of characteristics in a reduced order model. So moving forward, I'm going to be constraining my attention to this task. And so here we're interested in computing models that are able to tell us, and accurate in doing so, as a matter of fact, of telling us how output Y, a quantity of interest, changes in response to changing inputs and initial conditions. And so here, just schematically, we have a turbulent cavity flow. This represents, for instance, the flow inside the wheel well of an aircraft. And for instance, we might want to optimize the geometry of this cavity for aerodynamic performance. So the output could be the drag, and the input is our geometry parameters and different initial conditions for the fluid flow. And so we want to be able to predict Y in response to U and Q naught with our model. So that's the ultimate objective that we have, and that will determine the type of approaches that we must use for the purpose of computing models. Great. And so now this is the second. So that was the high-level motivation of model reduction. We're going to go into low-level motivation, and so why oblique projection? So now we're going to be constraining our attentions to linear encoders and decoders, and basically, if you notice, I've constrained them in a specific way. Specifically, the encoder is on the left is a left inverse of the decoder on the right. And so by this property, we can define the encoder and decoder define a projection P given by the decoder after the encoder. And a projection, as we all know, is a linear map from Rn to itself that is idempotent. And so why do we care about that? Why would we want to constrain the encoders and decoders to define a projection? This is a very nice property to have, because it means that we do not introduce a spurious drift in the latent space. So basically, you can imagine that if this property was not satisfied, I can encode and decode the state repeatedly and introduce a drift in latent space. And so we only want the latent space state to move because of latent space dynamics, not because I'm simply encoding and decoding the state. And so if I enforce the encoder and decoder to define a projection, then I'm good to go. So that's the motivation behind it. Okay, and then just as a note in passing, this is somewhat important. If the span of psi is equal to this, so the span of psi here is equal to the span of the encoder, the decoder, then the projection is orthogonal. Otherwise, we say it is oblique. So to get a better understanding, perhaps more like intuitively of what this is, I have a very simple example. So this is perhaps one of the most simple systems you can come up with. It's linear, has two states, and the name of the game here is to reduce the system to one state. And I do appreciate the irony here. We're talking about high-dimensional systems, wanting ROMs, and here I am with a two-dimensional state that I claim to be too expensive to simulate. Of course, this is just for representative purposes. But what are some of the features of the system? So this is, of course, stable with eigenvalues -1 and -10. But really, what makes this system difficult for the purpose of model reduction is the fact that the low energy state x2, this state decays very rapidly, has a strong impact on the state x1 through this off-diagonal term 20. And so, well, it turns out that we say that the state x1 is the dynamics of x1 are very sensitive to the dynamics of x2, even though the x2 has very low energy because it decays to zero so fast. So here I have just quickly simulated a few trajectories. And so I start from initial conditions like, somewhat far away from the blue line. And you see that it doesn't matter where I start the system from, all the trajectories are quite rapidly going to collapse on this blue line, which we're going to call our attractor, I guess, for lack of a better term. But also what I want to point out here is that they approach the blue line by following these trajectories that are more or less orthogonal to this green line, right? And so basically, so where's the catch here? So identifying the blue line is quite simple from data. You can just simulate a couple of trajectories. You can do something like POD or PCA that we're all familiar with. And basically, PCA or POD will tell you that the most energetic subspace is the blue one. In fact, all the trajectories collapse onto it. The difficult part is identifying the green line. So it's quite easy here because you can see it, but in a high-dimensional system, it's quite difficult to figure out this subspace that is orthogonal to the direction of the fast time scale. And it turns out that to identify this green line, you need the so-called adjoint. In fact, to draw this line, this is the subspace spanned by the left eigenvector of A corresponding to the slowest decaying eigenvalue. Okay, so let's now try to compute a reduced order model. We want to have a one-dimensional model that evolves on the blue line and is somewhat representative of what happens to the two-dimensional system. And so I start with an initial condition, and the first thing that one may try to do is say, well, I'm just going to orthogonally project my initial condition here onto the blue line and then evolve the system. So this is what the exact system does, and this is what the ROM prediction is. This is terrible, right? We see that for this initial condition, the exact trajectory approaches the origin from the right, but the ROM approaches it from the left. So at all times, the error with the exact trajectory is huge. If instead we project obliquely, we get a much better reduced order model. In fact, so we take the initial condition here. Instead of projecting it down, we will project it obliquely in a direction that is orthogonal to the green line. We get another initial condition for the ROM, and now we evolve it. And so we see that both the ROM and the exact trajectory approach the origin from the right, which is what we wanted. And also here by construction, the way that I made the reduced order model, the exact trajectory and the ROM trajectories will meet at the blue line at the exact same instant. So roughly from this point forward, there's zero error in the ROM. That's not always going to be the case, but it's just nice to have here. Great. So hopefully I've convinced you that if I look at initial conditions that are far away from the attractor that I want to project onto, we might need oblique projections to get accurate models. And just so you know, a lot of fluids, despite their complexity and their high dimensionality, they do behave like the simple toy model, and hence the reason why I chose it for representation. So what's the takeaway? The takeaway is that we might need oblique projections for model reduction, especially if the full order model is sensitive to low energy states. The difficulty here is that constructing appropriate oblique projections requires using the adjoint to identify the low energy states, directions, and so forth that the system is sensitive to. In the last third of the talk, we'll see that the adjoint might not always be available. For example, if we use commercial software or legacy codes, and so the added complexity of computing accurate models when you're using commercial software. And so just before moving forward, why does the adjoint tell us about sensitivity? Just a quick equation here. So suppose that we're interested in studying how the state x1, the most energetic one, varies as we vary the initial condition. Then x1 by the exact solution of LTI systems is given by this equation. And so we can compute the gradient of x1 with respect to x naught here in bold. And we see that this vector here, the gradient, which is now two-dimensional, lies in the span of e to the a transpose. So here you see that basically the gradient lies in the span of the adjoint. So this is why, if we think of gradients as telling us about sensitivities of the system, we sort of close the loop in the sense that adjoints tell us about sensitivities of the system. Excellent. Okay, so let's look at some actual formulations here. So Petrov-Galerkin modeling. So what is a Petrov-Galerkin model? I'm sure most of you know what this is. Again, we fall within this picture. We have our FOM, the full order model. So what we do in Petrov-Galerkin modeling with linear encoders and decoders, we basically define them to identify an oblique projection, and then we Petrov-Galerkin project the dynamics. And so here we see that this block in the middle is a function of phi, psi, but also f. With f is the full nonlinear dynamics. You can think of this as the spatial discretization of the Navier-Stokes equations for those of you who work in fluid mechanics. So the accuracy of this chain here, this ROM, is dependent exclusively now on phi and psi, actually on the subspaces that they span. So we ask the questions, how should we choose them for an accurate model? Okay, so perhaps the most simple, the most simplistic thing you can do is you can do POD or PCA. So we have a bunch of training data from a high-fidelity simulation. You stack it into a matrix, and you compute PCA. These are the directions of maximum variance or maximum energy of the data. And then we set the encoder equal to the decoder, and then we Galerkin project. So this is, by definition, an orthogonal projection onto high-energy features. Effectively, we're doing what we did in the first demonstration of the toy model. We're just orthogonally projecting an initial condition onto the span of the projection. And by the discussion we just had, you might conclude that this might not be the best thing to do from a dynamic standpoint. Okay, so we know that we need oblique projections at times. So POD doesn't give us that. What can we do? A very famous approach comes from linear control systems theory and is balanced truncation, introduced in 1981. All right, so we start from a nonlinear dynamical system, but we have to bring it into linear land, so linearize around some reference solution that is important to us, or it makes sense to linearize about. And we obtain our usual linear time invariant system, q dot prime is equal to a prime plus b u and so forth. And also here we do have a quantity of interest that we are tracking. And what we do in balanced truncation is we try to find a change of coordinates where the so-called reachability and observability gradients are equal and diagonal and balanced. And once we do that, then basically we have we end up with a diagonal matrix where the entries in the diagonal are ranked by importance, meaning that they identify the states that are simultaneously most controllable and most observable. So in those coordinate systems, it's quite easy to do a truncation, and we just say, well, we're going to throw away all the states that are non-controllable and unobservable, and we just retain those that are. So that's the procedure behind balanced truncation. I know this is not a lot of detail, but basically, but notice that for this change of coordinates, we're basically constraining the state to evolve on the span of phi, but we are identifying the feature C prime via oblique projection because we have this orthogonality condition. So basically, in this setting, the encoder is not the same as the decoder, so we implicitly define an oblique projection. This is nice because at least for LTI systems, we have an a priori error bound on the infinity normal of the difference between the ground truth input-output map and the reduced order input-output map. So this is quite cool because it's basically telling us that if you want to lower the error on the prediction, all you have to do is to retain more states. That's not necessarily true for POD, right? You can add one mode, but somehow the performance of the model decreases. And so that is because we don't have such a bound for POD projection. Okay, so we can use this balancing modes for nonlinear model reduction. And so we have an oblique projection now. There's a notion of we're capturing the sensitivity mechanisms of the linear system. The drawback is that this is only valid in the proximity of the equilibrium solution. So if we're looking to reduce the dimensionality of the system far away from this equilibrium, this type of procedure might not hold anymore, and the model might actually blow up in a nonlinear sense. So pros and cons. So here's the first contribution that we proposed a couple of years back during my PhD. This is work led by a former colleague and current friend of mine. This is called covariance. So this is covariance balancing reduction using adjoint snapshots. So we borrow from balanced truncation, but we try to relax its linear limitations. So you can think about this as a nonlinear extension to balanced truncation. Great. So we consider the usual full order system. And in this setting as well, we do care about some quantity of interest. So what we do is we define the following discrete time map. We call it capital F. And what it does is it maps. So we have trajectories of the nonlinear system. You can pick the state along this trajectory sometime t and some associated control input. And then this map, given that state and the control input, it will generate a sequence of outputs y at the current time plus something, tau plus 2 tau, and so forth. So we're generating, given initial condition and input, we obtain a sequence of outputs. Great. And so you can think of this basically as the nonlinear input-output map of the system. And so this is of course a very high dimensional map. and we seek a lower dimensional one, which we call f hat. And so we're trying to solve this optimization problem. We're trying to minimize the expected value of the norm of the difference between the ground truth sequence of outputs and the predicted sequence of outputs given by a reduced order model. And so, well, it turns out that if we fix P, then the optimal f hat is given by the conditional expectation, given the fact that we know PQ, and then all we have to do now is minimize the projection. This can be quite a nasty optimization problem, but fortunately, there's an upper bound that we can work with. It turns out that the cost function that we're interested in minimizing is upper bounded by this quantity, where now, importantly, we have these matrices WQ and WG. These are the state covariance matrix. So remember that F is a function of states Q along trajectories. And also we have the gradient covariance here. So this is the gradient of our sequence of outputs with respect to Q. So like it tells us how does the quantity of interest change as we change the initial condition, right? And so again, notice that gradients are appearing. And so there's a baked into this definition is some notion of sensitivity of the nonlinear system with respect to changes in the initial condition. And so it can be shown that this upper bound, basically the projection matrix P that minimizes this upper bound is one that balances WQ and WG. So basically it identifies a change of coordinates where these two matrices are equal and diagonal. And then again, that gives us the opportunity to identify states that are most controllable and observable in a nonlinear sense, if you will. And then it's quite easy to truncate. And so by defining P as follows, but using phi m psi, then the optimal phi m psi give us encoders and decoders that we can use for Petrov-Galerkin projection of the dynamics. So that's the first method, and I'll show results in a second. And then the second one is troop. You can think of this, it actually came first, chronologically speaking, but you can think of troop as a refinement on the previous method. And so the previous method gives us, like, basically optimizes a bound, but we can go a step further and we can actually ask for optimal projections that minimize some sort of forecasting error of the model. And so here's the optimization problem that we set up. We collect high fidelity data using our CFD solver, and we collect these trajectories. Then here's the cost function, basically. So we're saying that we're trying to minimize the mean square error between the ground truth trajectories and the prediction given by our reduced order model, subject to the constraint that our reduced order model is a Petrov-Galerkin model of this form. So clearly, what we have to find are the optimal phi m psi that minimize this constrained optimization problem. Well, it turns out actually that this problem is not a function of phi m psi themselves, not as matrices, but it's a function of the subspaces that they span. So we can solve the problem. We can cast the problem over the product of two Grassmann manifolds. These are matrix manifolds, and the space of r-dimensional subspaces of some ambient space Rn in this specific case. But those are just details. What I wanted to point out is that we actually don't need any type of automatic differentiation type of machinery to solve the system, because we know the gradient of J ahead of time. It turns out you can pencil and paper derive what the gradient of J is with respect to these parameters using adjoint-based optimization. So this is very cool because we actually have a closed form expression for the gradient. We don't need automatic differentiation, which can potentially be very expensive for these types of optimization problems involving dynamics. Okay, so let's look at a few problems. So the first one that we start with is I don't want this. So this is just a simple model problem. It has three states, x1 through x3. They're being forced by this input u, which is equal for all of them, and then we're interested in tracking the sum of the states along trajectories. So basically, it turns out that as in the previous example at the beginning of the slides, States x1 and x2 are the most energetic in the sense that the decay the slowest in the linear sense. So around the origin, the decay rate is -1 and -2. But they are non-linearly sensitive to state x3. X3 is decoupled from both of them. Is itself like its own linear ODE with a faster decay rate. But nonetheless, it strongly affects what happens to x1 and x2. And so what we do is we train all these formulations. We have Cobras and Troop that I just talked about. We have Petrov-Galerkin projection, balanced truncation that I both talked about before, and then our quadratic refinement on balanced truncation. I didn't talk about this, but you can think of this as a second order balanced truncation, if you will. And so these are training trajectories. So what you see is that Cobras and Troop are very, very capable of tracking the response Y, the output Y in response to inputs. By contrast, we have Petrov-Galerkin projection is basically just decaying monotonically to 0. It's incapable of understanding that there's a sensitivity mechanism underlying the system that causes like high amplitude transient growth. And balanced truncation does capture the transient growth, but there's a gigantic overshoot due to the fact that it doesn't account for nonlinearities, and this system is non-linearly sensitive to state x3, so it doesn't perform so well. Okay, so here that was a training trajectory. Let's see how it does on testing. And so we see that so the colors you want to look at are the blue one here, it's Cobras, and the green one is Troop. You see that for all these inputs, these two type of modeling formulations are keeping the error below 1e to the -2 for all times. By contrast, the other formulations do experience errors up to like of order 10 at certain times, and this is because they're either not accounting for the nonlinearity, or they are reducing the dimensionality, the orthogonal projection. They're completely disregarding the sensitivity mechanisms of the system. Here on the right, we're changing the type of input without retraining. Of course, we trained on impulses. Now we're testing on sinusoids. The story is the same. What we're trying to prove here is that we have actually learned the dynamics on that subspace, and we haven't just overfit to like an input, like an impulse type. Okay, cool. So let's actually look at a flow. Okay, so the next example is an axis symmetric jet flow. The Reynolds number is 2000. It's based on the jet centerline velocity. So you can think of these figures. You can think of a cylindrical jet, and what I'm plotting are the radial and axial coordinates. So just a slice out of the cylindrical jet. As I said, the Reynolds number is 2000. And it turns out that the flow is very sensitive to upstream disturbances on the shear layer. And these disturbances excite high energy downstream vortices. What I'm trying to say here is that if we introduce a very low amplitude perturbation here, like over the black dot, then eventually, due to the convectively unstable nature of this flow, this will cause very high energy vortex shedding downstream along the shear layer. And so this is you can think of this as like the flow being very sensitive upstream, but exhibiting like the basically the consequence of that sensitivity manifests itself downstream. This is complicated for example for POD to understand. Okay, so what we do is we train all the aforementioned methods here: Cobras, Troop, POD, and balanced truncation using impulse responses at different amplitudes. So we poke the flow on the shear layer with different amplitudes, and then we use our CFD solver to generate trajectories. And this is the energy of fluctuations around an underlying steady state that exists for that configuration. You see that this picture is basically telling us that the flow is highly nonlinear and highly non-normal, if you will. So basically, it takes a little bit of time for the energy to eventually ramp up. When it does so quite abruptly and by large amplitude, and then eventually it decays back down to 0, meaning that the vortices have left the computational domain. And so first thing that we want to do is we want to I have a figure that tells us the reconstruction error. So what we're doing here is we're taking testing trajectories here but they look more, well, actually, these are testing trajectories as well. So we're just statically encoding and decoding the state. And the lowest error is statically is achieved by POD, right? So this is no surprise. POD is optimal at compressing the data on an r-dimensional subspace. There's no linear projection better than POD at doing that, right? And so as expected, POD gives us the lowest reconstruction error out of all these methods. But then if we actually look at its forecasting capabilities, so this is the figure I just showed in the previous slide. But when we look at basically the forecasting capabilities of models obtained with different projections, we see that POD, that was the best one at statically encoding, decoding the state, is actually the worst one at dynamic forecasts. And that's because for this specific flow, you cannot use orthogonal projections because they completely accidentally disregard the sensitivity mechanisms of the flow. The other methods are doing better. And so we have like Troop well, Troop is the best of all of them. This is also intuitive because we minimize a forecasting type of loss. So by design, if trained properly, it should be the best of all of them. Cobras is also doing discretely, and all the other formulations are not doing great. I forgot to mention that here null is basically the null projection, meaning that for all times, the model is just predicting 0. So no matter what happens, we have, so that basically we see that a lot of models, even at early times, are capable of doing worse than a 0 projection. So if you don't get the underlying projection operator right, you can actually run into these types of issues. Okay, so what do some flow fields look like? So we have the full order model. This is time equal to 5. This is non-dimensional time. This is later time 15. And we see that Cobras and Troop are, they're a bit messy, I guess, but like they're getting the right features of the flow quite well. So I want to point your attention to the location of the vortices and the number of vortices that we see in the prediction. Especially Troop here is doing very well. We have a little vortex here that's about to shed, a little one that just shedded, and then these will come back downstream. And so Troop identifies this big one here, the shedding one, a middle one that has popped up at time 15. So we're actually doing pretty well in terms of forecasting where the vortices are, how many there's going to be, and what their intensity is. By contrast, POD is basically saying that nothing's happening to the flow if we poke it, which is not right. And BPOD, this is a variant of balanced truncation. It's more computationally efficient. It's not doing great. Remember, this is based on the linearization. The dynamics are nonlinear, so it's actually failing. And here it's blown up. So white means that the model is we got nans here, basically. Okay, so this is the end of the first half, I guess, and well, first 2/3, and gonna go into some non-intrusive modeling. So all these approaches were intrusive. What do I mean by intrusive? In one way or another, to assemble the model, you needed access to the underlying source code, especially if you want to have access to adjoint information. Basically, you need to be able to linearize your CFD solver around time-varying trajectories, and you need to compute the transpose of that linearization. And it's easier said than done if you have commercial software, for instance, where the underlying source code is proprietary. You cannot go in and modify it and extract the information you want. Or if you have legacy codes that are highly parallelized, you can think of like turbulent flow solvers that are just quite complicated to go in and modify and change to your liking to extract relevant information. So non-intrusive formulations are formulations that are purely data-driven and do not require access to the underlying source code. And so in that sense, they're slightly more convenient. It's less of a headache to use them. Okay, so I just defined what a non-intrusive algorithm is. And again, I said why it's important. Again, the necessary information to solve the optimization problems that I talked about a few minutes ago might not be available if you're using commercial software or legacy codes. Okay, so what do we do? So basically, now the name of the game is purely from data, so from high fidelity trajectories, how do we back out the components of the ROM? And so if you had a Petrov-Galerkin model, then G here would be obtained by Petrov-Galerkin projecting the dynamics. Here, if we only have access to data, then we, on top of learning the encoder and the decoder, we also have to learn the latent-space dynamics, again, purely from data, not relying on the underlying governing equations. I do want to stress that non-intrusive doesn't mean that you do not know what the governing equations are. Most of the time, we know we're solving the Navier-Stokes equations. We know what the parameters are, whatnot. Non-intrusive simply means that you cannot access the source code. And so if you happen to know that your system satisfies some symmetries, for instance, or if it's energy conserving, you can certainly use that information to your advantage and bake it into the optimization problems that we're going to be solving. But it's, you cannot access the adjunct, basically. That's what I'm trying to say. Okay, so perhaps the most famous way to do this, at least in the realm of projection-based model reduction, is operator inference. So operator inference goes as follows. So this is the same block that we've seen before. It has access to high fidelity training data from like a non-intrusive like black box solver. And what we do is we perform POD on this training data set, and we set the encoder equal to the decoder. And so basically, implicitly, we're compressing the data via orthogonal projection onto a low-dimensional subspace. Once we've done that, we have access to latent-space trajectories, and we can fit the dynamics. So basically, operator inference says, well, I know what Z is along training trajectories. I know what its time rate of change is. And so I'm going to assume that the time rate of change is a polynomial function of the state. So I can write it like this. Here, A, H, and B are tensors. And then they could just be optimized against data by solving a least squares problem. It turns out that if you set up the cost function, it's linear in A, H, and so forth. So it's a vanilla linear least squares optimization problem that we can solve. We know the exact solution to that. You can regularize it if you will, if you wish, and so very elegant. The trouble is that we are identifying the latent space coordinate Z via orthogonal projection. Again, so we're completely neglecting sensitivity mechanisms. Okay, so what was our idea? Our idea that we worked on like last year. So we said, wait a minute, what if we relaxed the constraint of identifying the encoder and decoder using POD modes? What if we also optimized the projection using data? So we simultaneously optimize all these blocks. Notice that the constraint that the encoder and decoders define a projection is already baked in the, like by construction. The encoder is the left inverse of the decoder. We have projection. So this is the optimization problem that we solve. The cost function is analogous to the one you saw before in Troop. So we're trying to minimize the mean square error between the ground truth high fidelity trajectories and the prediction given by the ROM. Now the ROM is no longer a Petrov-Galerkin one that would make the whole thing intrusive. That's what we're trying to avoid. We borrow from operator inference and we say, okay, well, the dynamics in latent space are polynomial, and we're just going to fit. We're going to simultaneously learn the tensors. So basically, we're simultaneously optimizing these parameters A, H, and B that are that define the latent space dynamics, the encoder psi, and also the span of the decoder phi. So this identifies basically a matrix manifold, telegraphic M. It's well known how to do optimization on matrix manifolds, so we leverage a lot of that literature. And again, the nice thing about this formulation is that the gradient of the cost function with respect to the parameters can be computed in closed form. And so, as I said before, we don't have to rely on expensive automatic differentiation. So training is quite cheap. We know what the form of the gradient is. We just have to evaluate it, and we can do that quite cheaply. The algorithm is almost embarrassingly parallel across training trajectories. So it's actually quite fast to train this even for very high dimensional systems. Okay, so first example we're going to be looking at is the complex Ginzburg-Landau equation. This is a 1D PDE. It's it's non-normal around the equilibrium. It's non-linear. It exhibits a lot of dynamical features that are similar to fluid flows, like wake flows, convectively unstable flows, and so forth. So what we're trying to do here is we have an input. So it's like here on the right-hand side, we would have a plus u. And so basically this input enters the dynamics like downstream around this location. So we're basically hitting the flow at this spatial location, x equal to -10. And then we want a model to tell us what happens to the system in this spatial location x equal to 10. So here C basically gives us like an output map. And so we train with 4 impulse responses. So we hit the flow at different magnitudes at this spatial location. Then we collect change trajectories given by the solution of these systems. And we want a 5-dimensional system. So here I think we had 400 states coming from the finite difference discretization of this ODE. So we go from 400 to 5. Let's see what we can do with this. So this is the average testing error across 25 testing impulse responses. So we have Petrov-Galerkin. It's just not doing great. Operator Inference also not doing fantastically. But then we have TRUP and NiTROM. So this NiTROM is the formulation I just described, non-intrusive trajectory-based optimization of reduced order models. So you see that both TRUP and NiTROM that are based on oblique projections are doing much better. The difference being that NiTROM is fully non-intrusive, right? So we didn't have to compute adjoints. We didn't need access to the underlying source code. We were just handed data, and then we just optimized against data without knowing exactly what code generated those data. It could have been finite difference, finite volume, finite elements. Doesn't matter. This is a profile of the output y along one of these trajectories, and you see that both TRUP and NiTROM are doing a pretty good job at tracking the time history of the output in response to that impulse. By contrast, Operator Inference and Petrov-Galerkin are not doing so great. Here, so we tested on impulses. Now we're going to be, we trained on impulses, and now we're testing on sinusoids. So this is sinusoidal input at this frequency. This is the fundamental frequency of the enforced dynamics, so the natural dynamics. And this is the second harmonic. See that both cases, NiTROM and TRUP for that matter, are doing a good job of tracking the input, the output. By contrast, the other 2 formulations can't. And then what we do is we look at another incompressible flow. It's lid-driven cavity flow, Reynolds number 8300. So here's the geometry. The top wall is being driven with velocity, non-dimensional velocity 1 from left to right. No slip boundary conditions at all other walls. And so if you wait long enough, the flow will settle onto this steady state of this type of recirculation vortex here. And we want models to predict what happens to the whole state of the system inside the cavity as I poke it at the top right corner. Okay, so these are change trajectories. We have 7 of them. We want models of dimension 50. I think the full order model dimension was 20,000, if I'm not mistaken, in this simulation. So we go from 20,000 to 50. So here, again, a typical signature of non-normal systems that are sensitive to low energy states. After we poke the flow, the state energy decays, but then it goes back up and then way back down because the origin is exponential, is asymptotically stable. And so models based on orthogonal projection will have a hard time capturing this type of behavior. Okay, so this is the training error. This is the testing error on the right. Again, plotting Petrov-Galerkin, Operator Inference, and NiTROM. The training, we're doing very, very well, but I mean, that's expected. Well, assuming you go to a nice local minimum, that is, it's not always the case. Testing, we're still doing pretty well. The error does go back up a little bit at the final time, but I mean, it's very low anyways. And remarkably, though, we're on average, we're lowering the error around that peak that I showed you before by roughly 2 orders of magnitude. So we're now actually capable of figuring out there's a very large amplitude transient growth before there's a sharp decay in the energy at one time. Now what we do is we trained on impulses as we've done so far, and now we test on sinusoids at different frequencies. And here I'm plotting the time history of the energy in response to those different inputs. And we see that for all forcing frequencies, the pink line, our new method is doing a pretty good job at tracking the energy of the output. And so not only do we get the long time behavior, but we're doing very well at capturing that transient, so that steep growth in energy before we settle onto a time periodic lens induced by the external force. These are some snapshots of vorticity fluctuations, FOM and NiTROM, and operator inference and Petrov-Galerkin. Petrov-Galerkin and operator inference are, first of all, they are underestimating the amplitude of the vorticity field, but they're also getting the phase wrong. So if you look at this blue vortex here, it's roughly centered at 0.5x. Here it's shifted by a little bit. By contrast, NiTROM is doing a pretty good job at both in terms of amplitude and in terms of phase of these vertical structures. This is another snapshot from a different trajectory. I think this is a lower frequency forcing, but the takeaway is the same. We're doing well both in terms of amplitude and phase of the vertical structures. Excellent. So conclusions. So we've discussed the importance of oblique projections for model reduction, especially when you want to have models that are capable of telling you what happens to a quantity of interest in response to varying inputs and initial conditions during transients. So that's very useful for the purpose of control design, optimization, where basically during, like if you're trying to optimize a controller, then a small variation in the control input will induce a transient that might be high energy. And so you do want to capture those types of dynamics. So we introduced two novel Petrov-Galerkin formulations, Cobras and Troop, that I talked about in the first 2/3 of the talk. And then we've gone one step further, and we asked how to relax the requirement that how do we get oblique projections without using the adjoint? And so we derived this NiTROM formulation. And yes, whoops. Okay, this was the acknowledgements slides. So just want to acknowledge mentors, advisors, colleagues, and friends over the years. And yes, thank you for your attention, and happy to take any questions.
Okay, speaks now. So, do you have any questions, Nico?
Thank you very much. Really impressive, in my opinion. I have a lot of questions, but I will leave it just by two curiosities. The first one is general. When you at the beginning mentioned the fact that for the computation of the oblique projection, we need that joint. That joint is needed just to compute the sensitivities, right? And so you can also, it is more expensive, but you can run your simulation and then collect the derivatives also by hand if you want. If you have a small control parameters, right?
Yeah. That's a very good point. Yes. So the adjoint just tells you about like how to construct the encoder, right? Not the decoder necessarily. But think about it. So if that procedure that you're proposing, which makes a lot of sense, right? It's like find a difference thing, basically, just to get the gradient, you find a difference. Like even if you have few control inputs, really what you're after is the encoder psi, which is n by r. So it still has the dimension of the full order system. And so you would need to run so many simulations that it's basically computational computation. So you're not computing the gradient of the output with respect to the input. You're computing the gradient of the output with respect to initial conditions. So regardless of the number of inputs that you have, you're still very tiny mesh. But excellent question. Yeah.
And regarding to that, I don't understand really much in the Cobra's algorithm.
Yeah.
Why you have defined the discrete time map in that manner? Because you have a control parameter that varies in time.
You might. It's not necessarily. Yeah.
Okay.
Yeah.
But you have f of q of u at t plus n tau.
Right. Yeah. So basically, the input to like f takes as an input your initial condition along the trajectory, and also like the sequence of inputs. You need to know that to determine the if you have a control system. So in the jet we didn't have a control input. Like it wasn't controlled. It was just the input to that map was just the initial condition. But if you are controlling the system, like in a control system, the output depends not only on the input but also on the time history of view. So yeah. So if the dynamics are influenced by a control input, you need to account for that. Yeah. Hope that answers it. If not, we can talk offline.
So just final
Yes, it will fit.
in trajectory-based optimization of oblique projection, you mentioned that you can leverage directly advanced differentiation in order to avoid to construct your joint.
Trajectory-based optimization. Is it the last formulation or the
last one would be
the last intrusive one?
yes.
Yeah. No, we do not use automatic differentiation.
Yes, but you need to compute the sensitivities through the solve, right?
Right. So it is intrusive and needs the adjoint to compute the gradient. Yes.
And you use just one difference. So you need a fully differentiable solver in order to do that.
Right. So yeah. So you could use automatic differentiation to differentiate the solver. What we do is this is the compressible number of Stokes equations. It's actually pretty easy to derive the adjoint by hand. So that's what we did. Yeah.
Compressible. Do you mean?
Yeah, compressible is more complicated. So like what I was trying to say is that yes, you can definitely use automatic differentiation to obtain differentiate the solver. Although you need to be careful about how you do that, because if you blindly automatically differentiate the cost function with all like the time steps with respect to the input, then basically your like autodiff graph will suck up a whole lot of memory, and so you need to be careful about that. Yeah. So the way we do it is very memory efficient. You could find ways around that, but
okay. So you have computed with the joint, right? So directly, but the continuous to the speed of it.
If I remember correctly, we did the continuous in that case, but you could do the discrete.
Oh, okay. Yeah, but the discrete is more complicated.
It depends on. I would say it depends on how you make your CFP solve. Yes, yeah, but yeah, I would say so. Like the continuous is just like at least in the solver that we used was more efficient. Yes, continuous was more efficient.
Thank you very much.